Okay, we're going to be looking at the reactions of aromatic compounds. Specifically, what we look at here are benzene, but these aromatic reactions are common with heterocycles and other aromatic compounds. It's just we're not going to be studying them in depth. We're just going to realize these are common reactions to all of the aromatics, and we're going to study benzene as we do that. So what happens when you take an aromatic compound that has a really great leaving group on it and you mix it with a really great nucleophile? Nothing happens. So what's going on? Well, for you to have that happen, you would have to break the aromaticity. And this is sp2 hybridized. We never have SN2 reactions occur on sp2 carbons because the orbitals are just not oriented in the right way for that to happen. So what happens when benzene is reacted with bromine? If it was a normal alkene, or just an average alkene, bromine would add across the double bond, but this does not happen. Why? It breaks its aromaticity. So what does happen? Well, if we add a catalyst, we actually get the bromine substituting the hydrogen here. So there was a hydrogen here. That hydrogen ends up attached to a bromide, and the bromine is added to the ring. So let's go and see what happens with this. This is electrophilic aromatic substitution. What you're actually having is an electrophile adding to the ring. We're used to nucleophilic substitution, where a nucleophile dives into an atom eager to gain electrons. But here you have an electron-rich aromatic pi system. It's going to repel nucleophiles, and what happens is it attracts electrophiles. You can have some nucleophilic substitution on a benzene ring, but it's not very common at all, and it takes some highly electron withdrawing groups on the ring in order for that to happen. So what we're going to see is aromatic compounds tend to do electrophilic substitutions. In the electrophilic substitution, the pi system is full of electrons and sucks in electrophiles. The electrophile adds to that pi system, and the positive charge of the electrophile is then distributed throughout the pi system. It's not on one atom in particular, so it makes the transition state not too high in energy. And then what happens is a proton leaves to restore the aromaticity. So what you actually have is a proton on the benzene ring is taken off in order to allow the electrophile to add. Except the electrophile adds first and then the proton leaves. So here's the general mechanism of electrophilic addition. Something that provides an electrophile. Of course, you have to have a counter ion to it. But there's an electrophile. The electrons in the benzene ring reach out and grab that electrophile. It makes this temporary non-aromatic compound, but that intermediate carbocation is stabilized by conjugation with the pi system here, and there are resonance structures that the positive charge can be here, here, and here, and because it's delocalized, that transition state of the carbocation is lowered in energy. Then what happens is the counter ion here will actually pick up the proton that comes off the proton leaving the ring, and when that proton leaves the ring, it restores aromaticity to this ring. So what kind of reactions do we see? We see something called electrophilic bromination. In electrophilic bromination, you have bromine and a catalyst shown here as aluminum bromide, iron 3 bromide. Aluminum bromide would also work. The iron will complex with the bromine molecule. Unless you have this catalyst there, there's going to be no reaction because it's through this complex with the bromine that you have addition occur. Here the complex is shown down here, and there's a number of different ways of putting this. You can actually show a positive charge on the iron and a negative charge on the bromine, and this bromine neutral, or all sorts of things like that. But the whole idea is that the electrons are being drawn into the iron, and so that makes this end of the bromine have a large positive charge on it. That large positive charge on the bromine here makes it very attractive to the electrophilic pi electrons in a benzene ring. So let's see what happens. The benzene ring can grab that bromine, which has a large positive charge on it, and it releases its electrons to this complex. That makes an iron 3 bromide. Some mechanisms draw this with the bromide still attached to the iron, which is fine. There is a complex that can form that way. And when you have this come off, this carbocation over here is stabilized by resonance, positive charge being able to move into 2 other places on the ring. And then quickly, aromaticity is restored by the proton leaving, and it's picked up actually as from the bromide to make hydrobromic acid. Electrophilic chlorination can occur in the same way, and again, aluminum chloride could be used here. But the reagents, chlorine and iron 3 chloride, are typical. It complexes in exactly the same way. The benzene ring reaches out and grabs that chlorine in the same way and then eliminates a proton to restore the aromaticity of the ring, and you get chlorobenzene instead. Okay, with iodination, you have a slightly different mechanism. Instead of making a complex that puts a large positive charge on one end of an iodine molecule, you actually make an iodine cation with an oxidizing agent. So either hydrogen peroxide or copper 2 chloride are used to react with the iodine to make an iodine cation. The reason an iodine cation can actually directly be formed is the iodine cation, the iodine is much larger, and so that cation is not as unstable with such a large atom where that positive charge can be spread out a little bit. So either the conditions of iodine with copper 2 chloride or iodine with hydrogen peroxide will allow iodination to occur. You can see that the iodine cation is the electrophile that adds to the ring, but in just the same way as the other mechanisms, what happens? The intermediate carbocation is stabilized by resonance with the remaining double bonds, and the hydrogen cation, or the proton, leaves in order to restore aromaticity. So you try it. Go ahead and see if you can figure out how to draw the mechanism for the bromination of benzene. And try real hard to do this on your own without looking at anything, and just see if you can recall the steps. And if you make mistakes, that's okay. You learn from mistakes. Well, the first thing that happens is that the bromine reacts with iron 3 bromide to make a complex. Here's the complex. This is the other way that I showed that the complex is made, where there's actually a positive charge on the bromine and a negative charge on the iron. When this complex bumps into the benzene ring, the pi electrons reach out and grab that bromine on the end, and the electrons that are in that bond jump to the bromine on the inside of the complex. This then gives you an iron 3 bromide, an iron tetrabromide anion that can act as a base and pick up the proton, releasing hydrobromic acid and regenerating the iron 3 bromide. When that proton leaves, it throws its electrons into the pi system, and the pi system is restored to an aromatic system. So what are the conditions that you need to change benzene to chlorobenzene? Well, you have to have chlorine and a catalyst. What's the catalyst? Well, a great one's iron 3 chloride. What do you need to change benzene to iodobenzene? Well, that's going to be iodine and an oxidizing agent. The oxidizing agent can be either hydrogen peroxide or copper 2 chloride.